Hello, hello. Answers. Okay, 9 o'clock. Good evening. Hello, I'm Layman. I am going to run through this last streaming session for this year before your HSC exams, and this section is on equilibrium constants. I'll touch a little bit on the Chatelier's principle, and then I'll also touch on acid dissociation constants as well as solubility constants, Ka values. So what is this? How many marks is this worth? It doesn't look like there's a lot of marks, but out of all the questions, it does scale in the top 5. So this is the 5th one, 4 marks out of your HSC. Pretty consistent over the last 4 years. Let's jump straight into it. Now, if you guys have any questions, feel free to jump on the comments and say, just ask the question. Stop me if you need me to, but there might be a bit of lag on the comments, so stop me whenever. Okay, so I'll quickly go through some of these equilibrium constants, and if we've got time, I'll run through acid dissociation and Ka values as well. So first of all, what governs equilibriums? Le Chatelier's principle. Now, I like to make this as short as possible because any sort of equation, equilibrium, shifting, all of that stuff, you really want to have this as a stock standard response for your answers. So, probably can't shift this. Okay, what does the Chatelier's principle state? It states that in an equilibrium, make it even shorter, that when a change occurs in an equilibrium, the system will shift to oppose it. Okay, so whether that's concentration change, temperature change, pressure changes, you need to state your Le Chatelier's principle in your equilibrium response. Now, today's session isn't really about that, but I'm not going to go through too many questions. I'm not going to go through any questions about Le Chatelier's principle today. So if you guys have any questions, concerns, please put it in the comments below, and I'll have a gaze through them and hopefully answer your concerns. But jumping on to this question, so question 6, this one's from Abbottsley Year 12 2021. Multiple choice, which KEQ value indicates a reaction where the products are most favored? Okay, so when you look at KEQ, so what is KEQ first of all? KEQ is our concentrations, so the product of our concentrations, how many there are, multiply them together to the power of whatever coefficients they are, over the power to the multiplication of the reactants. What determines where or which side is favored? We want to look at equilibrium as something in the middle and a spectrum from left to right. Let's see if I can get more space down here. Now, this spectrum this spectrum talks about two things, okay? It's very similar to what we've written for our KEQ, okay? So this side is reactants, and this side is products. If our KEQ value is large, we are here, okay? Large KEQ. If our KEQ is small, our KEQ is small on our reactant side, okay? Because if our KEQ value is big, that means our numerator here is big. If our reactants concentration is big, that means our denominator is big, which makes our KEQ small, okay? So we want a KEQ that favors the product, so that means we want a large KEQ. Which one gives us a large KEQ? So this is big, small, smaller, smallest, okay? So that means our answer is A. That should be pretty straightforward. 14. This question, Abbottsley 2021, question 14, multiple choice. HI gas can be decomposed in a reaction vessel at 445 degrees. The equation for this reaction is shown below. The KEQ value is 0.02. 2 HI gas, equilibrium H2 gas, I2 gas. The reaction vessel was sampled and found to contain this many moles of HI, this many moles of H2, this many moles of... Okay, this is a typo, because if that is QEQ, that means that's just KEQ, right? So our Q is typically at any point in time our products over our reactants, okay? Which is this. Now, how does that differ from our KEQ? Our KEQ would be this. Now, specifically, the concentrations of these guys are at equilibrium, right? So I'm sure you guys are aware of an ICE table or RICE table for some other schools. You will need to find the equilibrium concentrations for you to sub it into these values, okay? Anytime. And we want to see if our Q is either equal to KQ, greater or less than, okay? So what is that equal to? So it's, all these are concentrations. So what are the concentrations? We've got our concentrations perfect already. So 2 liters, 0.5 moles per liter, 0.1 moles per liter, and 2 squared. Okay, now for a constant, the units aren't that concerning. They're not concerning at all. So because constants are unitless, we don't need to worry, okay? If you guys have watched my other videos, other streams previously, I hammer on how much units are very important. For this one, I'll let you guys go for it, okay? So what is that equal to? 0.5 times 0.1 over 4. So that's 0.125, which is less than our 0.02, which is equal to our KEQ. So what does that mean? Q is less than KEQ. So it is either B or C. Now, which way will our equilibrium shift? Okay, we can draw our same spectrum again. Reactants, products. Now our Q is less than KEQ, so our Q is sitting somewhere around here, all right? And we want to get to our KEQ. So which direction do we have to point in order to get to our KEQ? We have to point this way, all right? So what does that mean? We want to end up producing more H2 and I2. So the answer is B, okay? Moving on, question 16. 2 moles of N2, 2 moles of H2, 2 moles of NH3 are placed in a 2-liter sealed flask and left to reach equilibrium. At equilibrium, the concentration of N2 is 0.8. What are the equilibrium concentrations of H2 and NH3? So, for this one, we need to write out our equation. Now, this one you guys should know already. This is our Haber process. Alright, we need to then do our ICE table. Now, ICE stands for initial, concentration, change, and equilibrium. Now, some people use RICE as well. RICE, the R just denotes the ratio, But not typical, but a way to make sure you use the right ratios when you do it in your change. Okay, so our initial is 2/2, which is 1 moles per liter. Our H2 is 2/2, which is again 1 moles per liter, and again our ammonia is also 1 moles per liter. Our change, this is based on the ratios. If it's a reactant, it gets consumed. If it's a product, it gets produced. So how do we denote that? Our change is, in this case, minus x. Our H2 in this case is minus 3x, and our ammonia is plus 2x. All right. So what does our equilibrium concentrations equal? So that will be 1 minus x, 1 minus 3x, and 1 plus 2x. Now x is just a mole, an amount based on the same ratios between your reactants and product. Okay, so we want to find out what x is, so then we can find we need to find x, so we can then find the concentrations of H2 at equilibrium and NH3 at equilibrium. So we're given that the concentration of N2 is 0.8 at equilibrium. So 1 x is equal to 0.2. That's great. We can then work out H2, which is 1 minus 3 times 0.2, which is 0.4, and also NH3, which is 1 plus 2x, which is 1 plus 2 times 0.2, which is 1 plus 4. So 1 plus 4, 1.4, sorry, and 0.4 gives us option B. Okay. Question 20 from Barker. 2020, question 20, multiple choice. Okay, how would the concentration of Pb ions in equilibrium with PbI2 solid be affected if the concentration of iodide ions were doubled? All right, so this one, okay, this one's sort of a Ksp question, right? So our Ksp, okay, so before we do Ksp, let's do our breakdown of what our reaction is going to look like, okay? So Pb iodide solid, and with our equilibrium, Pb2 plus aqueous plus iodide 2 iodides aqueous. So our Ksp value is going to be Pb2 plus bracket iodide square. Now, if we do our general ice table, we'll figure out our solubility on a typical saturated solution is going to be S times 2S whole squared, which will be 4S cubed. Now, noting that Ksp is a constant value, we can do the following. All right, so we can consider this to be equation 1, and then we can consider the second equation whereby our iodide solution iodide ions have doubled, so that means this value has times by 2. So what does that equate to? So that is 4S, and now 4S is 4S squared. Okay, we're just changing the concentration of our amount inside that. So what does that become? That becomes 16S cubed. Noting that that's going to also be some sort of constant, we can do 16S cubed over 4S cubed, which will give us 4. So that means that the 4 needs to be decreased somehow, and that somehow is by decreasing the solubility of our Pb. Okay, so the answer is D. Question 22, sulfur trioxide is made by the reaction of sulfur dioxide and oxygen in the presence of a catalyst. That's the equation. In a closed system, in the presence of a catalyst, the reaction quickly reaches equilibrium at 1000 Kelvin. A mixture of 2 moles of sulfur dioxide and 2 moles of oxygen was placed in a 4-liter evacuated sealed vessel and kept at 1000 Kelvin until equilibrium was achieved. At equilibrium, the vessel was found to contain 1.66 moles of sulfur trioxide. Calculate the equilibrium constant at 1000 Kelvin. Okay, that might need a little bit more space. Okay, so we've got the equation there. We've got our initial concentrations of these guys. And then we've also got the equilibrium concentration of this guy. All right, so what do we need? We need an ice table. So 2O2, 2SO3. Let's do our ice table. Our initial is 2 on 4, which is 0.5. This is also 0.5. Now our product is 0 at this case, because there's no, there's no products initially in the vessel. Now the change is 2x. For this one is minus x, and then for our SO3 is 2x plus 2x. So our equilibrium is 0.5 minus 2x, 0.5 minus x, and 2x respectively. So we want to ultimately find the equilibrium constant. So we need to find all these x values, sub them in, and then we can sub it into our KEQ expression. So we can find that our 2x is equal to 1.66 moles over 4 liters. Now let's calculate what that value is equal to first. We can do 1.66 over 4, which is 0.415. Now 2x is equal to that. That means x is equal to 0.2075. Now we can sub it into these individual values, which is 0.5 minus 2x, which is our 0.415, which is then equal to 0.085. Our concentration of O2 at equilibrium is 0.5 minus x, which is 0.5 minus 0.2075, which is equal to 0.2925. Now we just sub it in. We know our SO3 equilibrium concentration, which is just 2x, which is 0.415. So therefore, if we do our KEQ expression, what's that going to look like? We want to do our products to the power of whatever the coefficient is at the front of that equation, and then do our reactants, which is SO2 squared times the concentration of O2. Now what is that equal to? So that's 0.415 squared times 0.085 squared times 0.2925. Okay, 0.415 squared over 0.085 squared times 0.2925. That equals to 81.4952888 ... Now, I did say units doesn't matter, but the rounding does. So how many sig figs did we use? The lowest sig fig we used was, in this case, 3. So we want to round this off to 3 sig figs. But this value has no units. Okay? Great. Doing good for time. Alright, question 31. Dinitrogen tetraoxide can decompose into nitrogen dioxide according to the following equation. Below is the concentration versus time for the reaction system. The graph was produced using secondary data at a temperature at 22 degrees. Great, lovely graph. Time T1 is shown on the graph below. Calculate the equilibrium constant at time T. Alright, so the equilibrium constant is equal to the expression given by the products, so NO2 to the power of 2 over N2O4. So these are already in concentrations, lovely. I don't need to work out the concentrations. So NO2, that is equal to 5, and that is equal to 1.5. So this is just 5 squared over 1.5. Oh, okay, forgot about that. The units of the concentrations is at times 10 to the negative 2. So we need to do 5 times 10 to the negative 2 all squared over 1.5 times 10 to the negative 2. What does that equal? 5 times 10 to the negative 2 whole squared, 1.5 times 10 to the negative 2. So that equals 1666 ... Now we can round that off to 0.16, two significant figures, so 17. Again, unitless, but we want to state how many sig figs we use. At time T, the volume of the system was halved, keeping the temperature at 22 degrees. Continue the graph to show how this would change. This change would affect the reaction system and how the system would respond to this change until equilibrium is restored. Okay, first of all, two parts to this. The system has its volume halved. So halving the system means we are increasing. You can think of this as increasing the concentration, but in this case it's increasing the pressure, which in a way is a way to describe concentration. So the pressure being increased, volume being halved, means that our volume, our pressure is going to all of a sudden increase 2 times. Okay, so that's going to go from 5 to 10. This will go from 1.5 to 3. Okay, now because we've increased the pressure, to write a response for this, but for the sake of answering the question, increasing the pressure will shift the equilibrium to reduce the pressure, which will cause it to shift to the side with less gaseous molecules, which is our left hand side, or reactants. So if we shift to the reactants, that means we're going to produce more reactants, and on the other hand we're going to consume more products. So this will dip and this will increase. Okay, it's not needed for you to know exactly how much this increases by or decreases by, but the main aspect of this is knowing the volume has been halved. That means our concentration has been increased by 2 times. Okay, perfect. No questions. Question 24. Consider the following reaction taking place in a 2-liter close reaction flask at 25 degrees. A2 gas plus 2B2 gas gives you 2AB2. The following graph represents the change in the number of moles of each gas in the flask over the first 10 minutes. Using data from the graph, determine the value of the equilibrium constant from this reaction. Perfect. Alright, again, our KEQ is our products over reactants. So this is AB2 concentration of squared over A2 over B2 whole squared. Now these are moles, so we need to divide it by the volume here. So we can either work them out individually, or let's do a bit of a crammed one this time. Let's do the calculations of our concentrations inside the fraction. Okay, so it might get a bit messy, but hang on tight. AB2 is 0.8 over 2 liters, and that's whole squared. A2 is 2 moles, over 2 liters. That's just 1, perfect. B2 is 1.2 over 2 squared. So what does that equal to? 1.2 over 2, that's equal to 0.4444 ... which is equal to 0. How many sig figs? 3 sig fig, 3 sig fig, 0.4443 sig fig. Okay, so pretty straightforward. After 15 minutes, some B2 was removed from the system. At 20 minutes, the contents of the flask was analyzed, and the following data was obtained. Determine if the system has reached equilibrium at 20 minutes and describe the rates of forward and reverse reactions. That's a perfectly good question there. I like that. So we want to now find not the KEQ, we want to find the Q. So what's the Q? It's the same, but in equilibrium, we want to see where they are at now. Okay, so we still apply that same formula. They've given us in concentrations already, so we can just put those numbers in. 1.05 times 0.4 squared, which is equal to 0.535714 ... Now, compared to our KEQ, that's greater than our KEQ. So therefore, not at equilibrium. Okay, that's answering the first part of that question. Determine if the system has reached equilibrium. It has not at equilibrium at 20 minutes. Now we need to describe the rates of the forward and reverse reaction at this time. Now again, pulling out our spectrum, where should I do this? I'll do it here, squeeze it in there. Our Q is greater, so our Q is here at the moment, and therefore it wants to go this way to our reactants in order to reach equilibrium. So that means the reaction which is reverse is favored more so than the products. So we can comment that the rate of the reverse reaction is greater than the rate of the forward. Now, one of my students showed me a question yesterday which says there's no effect on the forward reaction. Very similar question, not exactly the same. Now, there are rates of forward in this case because it is an equilibrium. It does go back and forth, but the rate of the reverse is significantly higher than the forward. Okay, so we can't just say the forward, there's no forward reaction. There is, but there's smaller amounts of the forward reaction occurring than it is the reverse. Okay, so the rate of the reverse is greater than the rate of the forward. You can then mention something along the lines of producing more reactants in order to produce to achieve equilibrium. Okay, consider the equilibrium system involving the oxidation of nitric oxide. If the temperature was increased at time t, determine the effect on the position of equilibrium and complete the graph to show how the change will affect the concentration of reactants and products. Okay, great. This is another question, but now we're talking about heat. Now, forward is exothermic, given by the negative delta H. Okay, so that means our reverse is endothermic. Pretty straightforward there. So if we increase temperature, what does the Chatelier's principle tell us? It tells us we want to decrease the temperature. How do we decrease the temperature? We got to shift to the endothermic reaction in order to decrease temperature, which is our reactants. So the effect on the equilibrium position will be shifting to the endothermic reaction, aka towards the reactants, to reduce the excess energy. Okay. And then we want to draw on the graph how that will change the concentration of our reactants and products. Okay, so if we shift to the left, we produce more O2, less, we consume our NO2. So you can say, so it's very arbitrary, but NO would increase twice as much as your O. It's extremely difficult to draw on a computer. Okay, and our N2 would decrease approximately similar to our NO, approximately amount. Yeah, so you just need to show the reactants are increasing, the products are decreasing. Okay. Phosphorus pentachloride undergoes an equilibrium with our phosphorus trichloride and our chlorine gas according to the following equation. 0.2 moles of phosphorus pentachloride was placed in a sealed 2-liter container so that the equilibrium could be achieved. The container was found to hold 0.1 moles of chlorine gas. What is the equilibrium value for this reaction? Lovely. So that means we need to first work out our, so this is our initial PCl5 we got to assume this to be our Cl2 at equilibrium. Sorry, this is our moles, but then we can work out the concentration with our 2-liter vessel, so we can do our ice table. So our ice table is this. PCl2 is 0.1. So PCl5 is 0.1. Our initial for our product is 0. C is minus C plus C. Plus X plus X. 0.1 minus X is our equilibrium for PCl5. PCl3 is plus X, and Cl2 is plus X. Okay. At equilibrium, our concentration of chlorine gas, that means X is equal to 0.1 over 2, which is 0.075. So therefore our equilibrium of PCl5 is 0.025. Therefore our K EQ expression is not PCl5, of PCl3 concentration of, and concentration of Cl2 is PCl5 over PCl5, which is 0.075 squared over 0.025, which is 0.0225, which is A. Okay. All right. Last page of equilibrium questions, and then we'll do some Ka and Ksp questions. So one Ka question. At a certain temperature K, the following reaction is 75. We've got our initial moles of our O3, initial moles of our O2, and we have a volume of 5 liters. What is the direction of and the reason for the shift? Okay, so I'm going to do this all in the one equation again. So this will be O2 cubed over O3 squared. Our O2 is 1.5 over 5 cubed over 0.3 over 5 squared. So what does that equal? 1.5 over 5 cubed over 0.3 over 5 squared. That is 7.5. Again, so this one is less than Ke, sorry, not Keq. This one's not Keq, sorry. This one is Q, and that's less than our Keq. So that means it is B or D. Now, our spectrum. Q is less than Keq, so it shifts right. Okay, so that means our direction favored is right. 5. The equilibrium reaction, for this equilibrium reaction, the temperature is lowered and the amount of CiF3 then changed by 0.15. Now, I don't know why this is missing, but this is exothermic. The changes occur would be, okay, so if the temperature is lowered and this is exothermic, that means it's going to shift this way. So our CiF3 being changed by 0.15 moles is being deducted. Okay, so if we do our ice, mind blank there. We don't need to worry about what the initial is, because we're just looking at the changes here. Our options are just the change. So that means just looking at this equation, we're shifting to the right. That means the change is negative 2x because our ratio is 2. Our F2 is plus 3x and our Cl2 is plus x. Okay, so the change that we're looking at is negative 2x equals to negative 0.15, x is equal to 0.075. So that means our F2 is 3 times that, which is 0.225, and our x here is just that, but just plus x. Okay, so we have we want to decrease, so it's either C or D. We want to decrease this one, and we want to increase by this much and increase by this much. So our answer is C. Okay, great. We're down to our KA questions now. So hopefully you guys know how to answer your KQ questions, KSP questions now. So what is KSP? KSP talks about how much a certain salt, I like to use, let's use PbSO4. So, oops. So it looks at how much of each ion constituent is required for a particular solution to start forming a precipitate, okay? So our KSP only considers the ions, so it would be PbSO4 and SO4 2- for this particular case, okay? We don't worry about the solid, we don't worry about liquids because their concentrations don't change significantly and they don't have a concentration really, so it doesn't get included in our K expression. Now, question 33. A solution is made by mixing 500 milliliters of 0.12 NaOH solution with 500 ml of 0.1 molar of magnesium nitrate. Write a balanced chemical equation for this reaction. So NaOH aqueous plus MgNO3 2. Now this is a precipitation reaction. So what precipitate do we get? We got MgOH2 plus NaCl. Now, I'm not sure if you guys know the trick of this, but to determine whether this is the solid or this is the solid, you can either use one, SNAP. These are your ions which are always going to be soluble, which is your sodium, nitrate, ammonium, acetate, and your potassium. Okay. The second thing you can use is your KSP values on your data sheet. If it's on your data sheet, it means that it is either sparingly soluble or it's coined insoluble. Okay. In these cases, we would write the state of that particular salt to be solid. Okay. Now the balancing, I'm sure you guys across that. B. Determine if a precipitate will form as a result of mixing these solutions. Support your answer with relevant chemical equations. Okay, so the relevant chemical equation is this. Mg2 plus 2OH minus aqueous equilibrium with our MgOH2 solid. Now we need to first find the moles of our MgNO3 which is going to be equal to the moles of Mg2 plus because of 1:1 molar ratio, which is equal to 500 mils liters, 0.5 liters times 0.1 moles per liter, which is 0.05 moles. And then we want to work out the moles of our OH, which is going to be the moles of our NaOH. Again, 0.5 times 0.12 moles per liter, which is 0.06 moles. Okay, now the trick is we then need to find the concentration, right? Because our KSP is in the realm, our KSP is what we want to find, and our KSP requires our ions to be in concentrations. So how do we do that? Because we've mixed those two together, they've all of a sudden got different concentrations because we've added two volumes together. Now the volume is what we use, is the combined volume of these two solutions. So our Mg2 plus concentration would therefore be N over V, which is 0.05 moles over 0.5 plus 0.5 liters, which is 0.05 moles per liter. Our OH minus is also the same, 0.06 moles over 1 liter, which is 0.06 moles per liter. Okay, I might need to find a data sheet. So while we find a data sheet here, let's keep working on this. So our KSP, in this case, we want to try to find the ionic product, which you can also use Q. So in this case is 0.05, sorry. In this case, the ionic product would be Mg2 plus over Mg2 plus times the concentration of OH ions squared, which is 0.05 times 0.06 squared, which is equal to 1.8 times 10 to the negative 4. Now our KSP value, of magnesium hydroxide is 5.6 times 10 to the 12th. Okay, so is that greater or equal, or is that greater or less than 5.6 times 10 to the negative 12th? That number is greater. That means it's greater than our KSP. So same spectrum that we have, or very similar spectrum that we have, the KSP determines whether something will be soluble or not. Anything bigger is going to be precipitating, and then anything smaller will be in ions. So because this Q value sits somewhere here, it's going to be a precipitate. So therefore, precipitate will form. Okay. The molar solubility, great. The molar solubility of this is 1.3 times 10 to the negative 5. Calculate the KSP of this at this temperature. Perfect. Okay, so what that's saying is Ba3PO4 bracket 2 ionizing is 3Ba2 plus PO4 3 minus, and 2 of those, right? So the balance, the charge is balanced, which is great. Now the solubility is how much of this particular salt ionizes into your ions. Okay, so we need to do an ice table here. You can do an ice table, or you'll find the trickery that you won't need it, but that's all right. Let's go through the ice table first. Now initially there's going to be 0 concentrations of these guys because your salt hasn't been ionized just yet. The change is your solubility based on the molar ratio. So if 1 mole of this solubilizes into your ions, how many barium 2 plus ions would you expect? You would expect plus 3s, and for PO4 you would expect plus 2s. So your equilibrium is 3s and your equilibrium is 2s respectively. Alright, so our KSP value is going to be Ba2 plus concentration cubed times the concentration of PO4 3 minus squared. So that's just 3s cubed times 2s squared, which is 27 times 4 is 1. Don't trust myself, got to use the calculator. 108s to the power of 5. We know s to be this, so KSP is equal to 108 times 10, 1.3 times 10 to the negative 5 to the power of 5. Okay, so what does that equal? It's going to be a hugely small number. Power of 5. 4.009964 times 10 to the 23, which we round to 2 sig figs, which is 4.0 times 10 to the 23. Okay. That's KSP. The two really generic types of questions you either get, you're mixing, using your KSP to see if it's precipitates forming. You've got finding your molar solubility, or you've got your molar solubility trying to find your KSP. Okay. Now, the last type of question I wanted to go through is this Ka question. I thought this one was quite interesting. It really hits the assumptions how you can, make it a little bit easier to solve and really understanding acid dissociation. Okay, so hydrogen sulfide in solution is a diprotic acid and ionizes in 2 stages: stage 1, stage 2. A student made 2 assumptions when estimating the pH of 0.1 molar solution of H2S. The pH can be estimated by considering the first ionization reaction. The second, the concentration of H2S at equilibrium is approximately equal to 0.1. Okay, now I'm going to go through the second one first because that's the typical one we always see. Why can we assume the concentration of H2S equilibrium is the same as H2S initial? Very simple. I tell my students there's 3 things. Okay. Oh, it's 2 things. 3 things. This one is a weak acid. Okay, if it has a Ka value, typically you can denote it to be weak. It's a weak acid. That means it's got a low dissociation, meaning your S value. So when you do your minus S value, S is less than the initial concentration. So therefore, as a result, you can say that to be true. Okay. Now, I'm not going to do this, but if you want to prove this, if you want to say this, you can do your ice table, and your equilibrium concentration for that will equal to your 0.01, which is your initial of your H2S, minus S. Okay, but we've made the assumption that S is very, very small compared to your initial concentration, which means you can make this statement happen. Okay. Now the first one, the pH can only be estimated by considering the first ionization reaction. Sorry, it can be estimated. You can just look at the first one because of the magnitudes of these 2 numbers. All right. So you can see that the Ka for your first one is 6 magnitudes more than your Ka for your second reaction. So what you typically see happening is your first reaction dissociating. Your second, in comparison, is low. So what you expect is your H3O or your H plus ions is going to mostly come from your first reaction. Okay, so that's our justification for assumption 1. So we can say the Ka in first ionization is greater than our Ka in our second ionization. Okay. Now, using the 2 assumptions given above to calculate the pH of a 0.1 solution of H2S, so we want to calculate the pH. Okay, this is again another stock standard question that you might get, is you get a Ka value, you get an initial concentration of your acid, and then you want to find the pH. Okay. So how do we do that? Let's write out our Ka expression first. Our Ka is exactly the same as our equilibrium constant expression, again without the water. Okay, so we do our products, and then we do it over our reactants. Now we can do our ice table. Let's do an ice table, okay, because it fundamentally falls back down to our ice table. So what does that look like? Now we don't worry about water in this case. So our initial concentrations initially, our change is negative S, HS minus is plus S, S. So therefore our equilibrium is 0.1 minus S, S, and S. Now I'm actually going through this. So what does our Ka expression look like now? It looks like S squared over 0.01 minus S, and then using assumption 2 explanation, we can say H2S is a weak acid, therefore low dissociation, and therefore S is less than 0.01, or in other words, S is very small. Therefore, Ka is just S squared over 0.01. And then we can then isolate S, which is the square root of 0.01 times Ka. Now we know our Ka, which is our 9.6 times 10 to the negative 8. We can just square root that. And what do we get? We get 3.09386677 times 10 to the negative 5. K again doesn't have any. Sorry, what are we trying to solve? Sorry, we're trying to solve for S here. Sorry, S is the solubility or ionization. So this one is, what does S equal to? S is actually equal to our concentration of H3+. So we use this, we'll sub it into our pH equation, which is on the data sheet if you guys forget. But hopefully you guys have used that long enough to memorize that off by heart. pH is equal to negative log base 10 concentration of H3O or H+. They're both the same thing, which is equal to negative log 10 of that number, which is equal to 4.508864 ... Now, there's something special we need to do for pH. Whenever we're calculating the pH and we're rounding it off, we want to look at the number of sig figs, convert that to decimal place, and round our answer to that particular decimal place. So the number of sig figs, the lowest number of sig figs we used here was 2. So we used 2 sig figs, so we want to round that off to 2 dp. So that's 4.12 dp. Okay. Is there any acronym for equilibrium? Super Jelly Collision 17, hello. I'm not quite sure of what you're trying to ask in your question. Is there any acronym for equilibrium? In terms of the expression, in terms of the constant, do you care to explain or clarify what you're trying to ask? While we wait for the response, that's practically it. That's all the questions I really wanted to go through today. I do have a couple of final statements I wanted to make and give you guys, and basically, good luck. I've purposely not done tomorrow's session for you guys to put your heads down, study without any distractions. I believe I am a distraction, but hopefully over the last couple of days I've given you guys enough knowledge and a little bit more confidence in what you're doing in chemistry. Best of luck. And like for the constant of KEQ, Super Jelly Collision 17, is there any acronyms for the equilibrium constant? Do you mean in terms of just how the expression goes, like KEQ equals to your concentrations of your products and reactants? Is that what you mean? Again, feel free to revisit any of the other streams that I did for the last couple of days. Obviously, no obligations. The answers to the questions for the ones I haven't done should be in the slides. Should be in the link underneath it. Hopefully, it's helped. Super Jelly Collision 17. Try to memorize that. Reactants over products over reactants. Okay, that's all you really need to know. And if there's more than one product, more than one reactant, you would subsequently put your other reactants next to each other. So for example, Super Jelly Collision 17, sorry, you can do this. Okay, I like to just usually use this example. So your KEQ for this expression would just be your products. the coefficients come here, and then so they're all going to be the base of your reactant or product, but the coefficients just come up as powers. Okay, so if you want to just write this down in your notes, try to memorize it for the next 36 or so hours you guys left before your HSC, and apply that to whatever equation you get. Yeah, so Super Jelly Collision 17, if you have any other questions, feel free to leave a comment for me in the comments below. I'll try to answer it before your exam on Friday, hopefully tomorrow morning. But yeah, that's it for today, and that's it for this year. Good luck with chemistry, good luck with any other exams you might have, and you guys deserve it. Enjoy your break before you start uni, before you start on with whatever you guys are moving on to after HSC. So best of luck and get some good night rest. Okay, thanks very much guys, have a good night. Thank you.